All right, gentlemen. Um, Now we will continue studying our differential equations, about differential equations. So the last chapter we talked about power series solutions of linear differential equation, especially the second order, right? And also actually I saw some problems and shared with you. So we just only studied 6.1 and 6.2. That much is enough. We just studied how to find the power series representation of, what is it, the solution of differential equation about regular points. Okay, so you are expected to study it's chapter 6.1 and 6.2. So today I will start this chapter 7. That is quite big chapter, but I try to cover this in 2 weeks. Okay, and some examples maybe as a compensation I will record it and share with you on YouTube. Otherwise, we do not have much time, only 2.5 weeks left, maybe 2 weeks, and I will do some compensation during the prep week. Okay? So this chapter 7, is about the Laplace transform, one of the very powerful tool in differential equations. Okay? So we will talk about it is mathematical part. What is the mathematics of this Laplace transform? It has a lot of application in engineering and some other branches of science, okay? But here we will focus on what is it and how do we use it, how do we calculate this, and how we apply this to the problems. So we will start with the definition of the Laplace transform. And after that, today, maybe if we have time, we'll talk about inverse transforms and transforms of derivatives, okay? And some other things we will continue tomorrow, right? Operational properties, and we have here number 1 operational properties, number 2 the direct delta function. I will see, okay? If you have time we will study this, otherwise you will study yourself. And systems of linear differential equations. Okay, that is what we have. So we will start with the definition of Laplace transform. All right, so what you have to know here is we are going to use this improper integrals a lot. So I'm sure that you didn't forget this, but still, if you get stuck, you need to open a book or notebook, whatever it is, you need to review this improper integral, okay? With infinite limits of integration by parts and partial fraction decomposition. This is also what you studied in calculus 1 or 2. Okay, so we are going to use them very frequently. And also we know that in elementary calculus you learn that differentiation and integration are transforms. What does it mean? It means that by differentiating a function we are transforming this into another function, right? For example, if you are given x squared and if you differentiate this, we will get 2x. That is completely different function, right? And also in a similar way, here we have, for example, x squared. If you integrate this, right, it is transforming this function into another function. Actually, we call this a kind of transformation, right? Transforming, because this integral operation, right, transforming this function into another function. Here, Laplace transform is something like this, but it's quite different, and it is very, very handful or useful tool to solve linear differential equation. Okay, that is actually, we'll see there's some examples, some problems we cannot solve them by using the techniques and methods that we have learned so far. Okay, but you will see that by using this Laplace transform, especially the differential equations with boundary conditions, okay, it is very powerful tool to solve those kind of equations. Now let's start with and also this one, let me just remind you, is about linearity of differential operator and linearity of integral operator. Okay, that means that we know that if you differentiate the linear combination of two functions here, that is f and g, right? F and g, so is the same as first differentiate, and after that, that is the derivative of linear combination of two functions is the same as the linear combination of the derivatives of these functions, right? Here we have f prime. First, linear combination, differentiate or differentiate each separately and write the linear combination. They produce the same thing. That is the most important property of linearity. Also the same thing for integral. Here we have alpha times f of x plus beta times g of x is the same as alpha times this thing, right? Integral of f of x dx plus beta times integral of g of x dx. And why is it given here? Just to understand the similarity between this differential operator or integral operator and the Laplace operator or Laplace transform. Okay, because also Laplace transform, it possesses linearity. It has also linearity property. Okay, all right. So the definite integral, such as, let me just consider this integral from here, as you see here, this definite integral limits that's from a to b. Here we have capital A, K, S, T, f of t dt. What is it? That means that we are given here a function of two variables, right? If we just take this one as like our k here is something like f, x, and y. And let me just write here the small f. Okay, here we have something like this. It is a function of s and t. And is multiplied by another function. It's just a function of single variable, right? But here we are differentiating this with respect to t, right? So if I integrate this, what I get here? Here we will get something like this, right? We get something here, let's say capital F with respect to S, right? Why? Because this one is nothing to do with t, right? This t is changing from A to B. Still, this S remains, what is it? As a variable. All right, now we are going to talk about something special, okay? And also Laplace transform is something similar to this, okay? Here we have a function. Now we're just going to take that as e to the power minus st, and that is a special transform that is called Laplace transform. So now imagine that's, this is the definition of Laplace transform. Assume that we are given a function f, okay, that is defined for all the numbers, all the non-negative numbers. That is on this interval, okay? And by saying this, we are not saying that it's not defined when t is negative. When t is negative, it may be defined or it may not be defined. But here, what we need here is, we are sure that we are just considering functions which are defined over the non-negative numbers, interval, right, from 0 to positive infinity. So we are introducing Laplace transform as this. So here, this is some kind of curly L. Here we have curly brackets. Okay, this is how we use this. Here, F. Now we are transforming this function into another function. Okay, so Laplace transform of F is this integral from 0 to positive infinity. That is improper integral. Here we have e to the power minus st f of t dt. So it's said to be the Laplace transform of f, provided that the integral converts. Because this is improper integral, and also if you remember from calculus, it may converge or it may not converge. That means that it may be convergent or it may be divergent, right? And here, of course, we are primarily interested in convergent integrals. Okay, if it is divergent, we have nothing to do. And when it is divergent, also for some special values of s. Now, if we evaluate this, what do we get here? Actually, as you see here, we have a function here like this k s t, right? It's a function of two variables, s and t. This f is a function of t, and we are integrating with respect to t. So if we evaluate this, what we get here? We get another function of s. Okay, so what is happening here? Here we are given a kind of function that is defined for over this interval, right? And here we have f, right? And by applying some kind of special transformation, that is our Laplace, right? And we are just mapping this over something here. That is capital F. and this one is f of t. This one is capital F of s. All right. Now you will see that actually why we are doing here. The main idea here is assume that here we are given some kind of differential equation. Let's say a sub 2 y double prime plus a sub 1 y prime plus a sub 0 y. On the right hand side, let's say we have f of x or g of x, anything. Okay. So now here our x or t here, let's say it's f of t, doesn't matter. I can write f of t, but this is different t. Okay, this is different f. Let me just write here g. So actually now we need to solve this differential equation here, right? And I can find the value of y here. Okay, by using this Laplace transform, first I will transform this f into here, and I solve this differential equation here. If I can find this f by just applying it as inverse, then I can get back to this field, this space, and find it is, what is it? Suitable matching, right? This f, by applying this inverse, I can get this original y. This is what we are going to do actually. Here, first, I will just transform this into this space. And here, I will solve our problem, okay? And here, I will get the mapping of here, y. Here we have y, right? What is the mapping of y? It is something here. If I know it is mapping here, this capital F, using this inverse operation, I can get this y. And you will see that when I just solve this differential equation here, it is much easier than solving here, okay? That is one of the biggest contribution of this Laplace transform to solving this differential equation. All right, guys, we'll get back to this soon. First, let's try to understand this definition. All right, and also we'll practice some questions, some problems. What are the Laplace transforms of those functions? For example, let's say evaluate Laplace transform of 1. What is it? Here we are given a function f of t that is constant function, and we know that that is defined right over this interval. Actually, it's defined everywhere, but I'm sure that also it's defined here. So now I can write it as Laplace transform. So Laplace transform of 1 is equal to, using the definition, here we have 0 to positive infinity, e to the power negative st times our f of t. What is f of t? Is equal to 1 here. Here we have dt, right? That's equal to actually improper integral. How do we solve this? Here, I will introduce another variable. Let's say this b goes to positive infinity. Here we have from 0 to sorry. So here we have b, right? Here we have e to the power minus st dt, right? And that is equal to limit when b goes to positive infinity. We now have to integrate this. That's equal to minus 1 over s times e to the power minus st, right? From 0 to b. This is how we evaluate improper integral. Okay. So now if you evaluate this minus 1 over s is just nothing to do with b, right? It's not dependent on b, so I can just take out using the property of limit. So here we have minus 1 over s times. What we have here? Limit as b goes to positive infinity, right? And here we have e to the power minus sb, because now t is equal to b, minus when t is equal to 0, e to the power 0 is equal to 1. Here we have 1, right? Now, when does this limit exist? Actually, if s is positive, right? So if s is positive, what happens here? If s is positive, here we have e to the power minus sp. Here we have e to the power minus sp, which is equal to 1 over e to the power sp. And that approaches 0 as, what is it? B goes to infinity. And here providing that s is positive, right? If s is negative, what happens here? If s is negative, This negative s will be positive. When we go to positive infinity, also this goes to positive infinity, right? This limit does not exist. It's not finite here. That's why now I'm adding condition here. All right, here this limit exists if this b, right, when it goes to positive infinity, for this limit to be finite, right, this s must be negative, positive. So if s is positive, when b goes to positive infinity, this is equal to 0. Here we have negative 1 times 1 minus 1 over s. That's equal to 1 over s. So our condition here is s must be positive. Okay. Now, actually, we need to adopt this notation. Now we are going to use this a few more times. So instead of this limits notation, let's say this limit as b goes to positive infinity. Here we have f of b. Okay, let me just not like this. Let me just write here. All right. Integral from 0 to b. Here we have something here. Okay, dt. I will just write it as, here we have f of t from 0 to b. Okay, we are just adopting this notation. All right, usually in math we do not write this. First, when we are calculating improper integrals, I need to use limits. But just here to save time, okay, to do our calculation faster, instead of this limit, I'm going to write this notation. Okay, that is the first example. Let's say another example. What is the Laplace transform of t? That means that here we are given our function f of t is equal to t, and we know that this function is defined over this interval, right? So Laplace, here we have Laplace transform of t is equal to integral from 0 to positive infinity e to the power minus st times f. What is f? Is equal to t. That's equal to dt, right? And now, how can I do this? I can just do this by, what is it? Integration by parts, right? First, if I just bring this inside, I can write it as minus 1 over s integral from 0 to positive infinity. Here we have d e to the power st, right? Here we have u, here we have v, which is equal to minus 1 over s, open a big rectangular bracket here. Here we have t times e to the power minus st. Here we have from 0 to positive infinity minus, right? And from here we have 0 to positive infinity. Now we need to interchange these two functions. Here I need to write e to the power minus st, and here we have dt because t comes inside, right? All right, this part you are familiar. Just previously I have calculated, right? It is the same thing as Laplace transform of 1. This thing equals Laplace transform of 1. And here, it's exactly the same thing here, right? And that's equal to what? 1 over s. So I can use this 1 over s. This thing is equal to 1 over s. And how about this limit? As you see here, if s is positive, right? And when t goes to positive infinity, here we have t over e to the power st. And when t goes to positive infinity, if s is positive, this thing, right, it grows exponentially. That grows much faster than t is equal to 0. And when it is 0, also is equal to 0. So here we have 0. What we have here equals minus 1 over s. Here I have 0, right? Minus this thing, right, is equal to, we have just calculated, 1 over s. And if you simplify this, that is equal to, so Laplace transform of t is equal to negative 1 over s times negative 1 over s. That's equal to 1 over s squared. David, are you there?
Yep, sir, I'm here.
You can hear me well, right?
Yes, sir. Yes, sir.
Very good. Okay. Continue. Another example. Here we are just warming up and getting used to, what is it, using the definition. Another two examples here. Let me change my marker color so that you don't fall asleep. A. So we need to evaluate the Laplace transform of this function. So our f is, what is it here? F function is e to the power minus 3t. And in this case, our, let's say, g function is e to the power 5t, right? So we need to evaluate Laplace transform of e to the power minus 3t, okay? So if we are given the definition, now the question is, how can I transform this function into another function? And using the definition. That is what we are trying to understand here, or practicing. So again, immediately, what is it? That is defined as integral from 0 to positive infinity. Here we have e to the power minus st times e to the power minus 3t, right? And here we have dt equals integral from 0 to positive infinity e to the power. Here we have tt, common factor, and bases are the same, right? Just e. So I can write it as minus s plus 3t. And here we have dt, right? And if you remember at the beginning, the first example, when we have just e to the power st, here we have times 1, right? Laplace transform of 1. What was it? It is just 1 over s. But instead of s, everything is the same. But instead of s, here we have s plus 3. So that is just equal to 1 over this thing, right? So that's equal to, we can evaluate this, but you get the same thing. That's equal to 1 over s plus 3. Okay, now you will see that in general, if we have a here, for example, let's say e to the power at. What is it? It is from 0 to positive infinity, e to the power minus st times e to the power at dt. That is equal to 0 to positive infinity, e to the power minus, here we have s, minus st plus 18. Take this t out and also minus out. What we have here? Minus s minus a, s minus a, t. Minus s, minus is plus s. Here we have 18. And here we have dt. It's exactly the same thing, right? As if here we have our function is 1. Instead of s, we have s minus a. So what do we have here then? In general, that's equal to 1 over s minus a. So Laplace transform of e to the power at, or it is representative in another space, it is this. Or in another domain or another range, whatever it is, in another space, okay? It is how they are connected. By this Laplace transform, these two functions are connected like this, okay? All right, now, since we get this general formula, now using this one, I can evaluate this. Here we have Laplace transform of e to the power 5t equals, right? And what we have here, instead of a, right? Instead of a, here we have 5. So just using this thing, that's equal to 1 over s minus 5. So Laplace transform of e to the power 5t is equal to 1 over s minus 5. All right, another example. Here, I never used this color. Okay, let's just use it here. Okay, we need to find here this f of t, right? That's equal to sine of 2t. Guys, also we are going to get the formula, but here, since you understand the definition, I'm just going to get the general formula. Then I can evaluate this. Instead of 2t, let's say we need to evaluate our function is sine of at. And now we know that this function is defined over this interval, right? Actually, it is defined for every real value of t, and also particularly is defined over this interval. So now if you evaluate this, the first step, Laplace transform of sine at. Okay, That is equal to, by the definition, from 0 to positive infinity, right? Here we have e to the power minus st times what we have here, our function f of t. That is sine of at dt. Okay. So again, how can I evaluate this integral? By again, integration by parts. So that is equal to, here we have integral from 0 to positive infinity, e to the power minus st times, bring this inside, right? Here we have d, here we have cosine of at, right? But actually, if you just differentiate this, we will have here minus a times sine of at. So here I need to divide by 1 over a. So minus 1 over a, right? It will actually balance this. When I differentiate this, I will get back the original expression here. Continue. Equals, let me just keep this minus 1 over a here. Okay. From brackets. How they evaluate this? That's equal to e to the power minus st times cosine of at, right? From 0 to positive infinity minus integral. Here we have cosine of at and d e to the power minus st from 0 to positive infinity. All right. Okay. Equals, here we have minus 1 over a times. Again, guys, you should be really fast at calculating this one, right? Here, when it is positive infinity, here we have cosine of at over e to the power st. Now here, again, this limit exists if s is positive. Now just keep in mind that s is positive. So this thing, when it goes to positive infinity, this thing is equal to 0, right? 0 minus, when t equals 0, here we have e to the power 0 times cosine of 0, that's equal to 1. Minus, now here, if I just bring this out, right, minus s comes to the front. With this minus, it is plus s times integral from 0 to positive infinity. Here we have e to the power minus st times cosine of at. And here we have dt. Okay. One more thing left. Continue. Here we have negative 1, right? And let me just keep this. Here we have, if you multiply this, minus 1 over a times minus 1. So here we have 1 over a. And here we have minus s over a times. Okay. Now I will bring this inside one more time. So if I bring this inside, what we have here? It is sine of at. So I need to write here 1 over a times integral from 0 to positive infinity e to the power minus st. Here we have d sine of at. Okay. So that is equal to, here, let me just write something here. So we know that Laplace transform of this function, right? So Laplace transform of this f, that is f of t, if it exists, that's equal to capital F of s. Assume that Laplace transform of this function is capital F of s. So on the left-hand side, this thing, I'm trying to find this. Here we have f of s is equal to what we have here, 1 over a minus, here we have s over a squared times, right? Now, again, if you just bring this out, if you evaluate this, what we have here e to the power minus st times sine of at from 0 to positive infinity minus integral from 0 to positive infinity. Here we have minus s of t. Okay, we need to interchange these two things, right? So here we have sine of a t d e to the power minus s t. Right? Okay, so here we have f of s equals, here we have 1 over a minus s over a squared. Now if you evaluate this, when t goes to positive infinity, this thing is equal to 0. Minus, when t equals 0, here we have e to the power 0, that's 1, sine of 0, that's equal to 0. Here also we have 0. Minus, now if you bring this outside, again minus s comes to the front, that is plus s times integral from 0 to positive infinity e to the power minus st times sine of at. And here we have dt, close the brackets. Okay, so now if you look at here, this part, what is this? It is our original expression, right? From 0 to positive infinity, e to the power minus st, sine of at dt. So here we have 0 to infinity, e to the power minus st, sine of at dt. So this thing is equal to our f, because that thing is equal to f, right? That is equal to f of s. So now just I need to solve this equation for s. So if you solve this for s, what I have here? Here we have f of s is equal to 1 over a, that is 0, 0, minus, right? Here we have s squared over a squared times, that thing is equal to f of s. All right. So now, if I just take this to the left-hand side and take this f and divide both sides by this expression, what do we get here? Then here we get here that f of s will be equal to, here we have, what we have here, a squared, right? A squared, so a squared, a squared plus s squared, right? And here we have a. So here we will have a over s squared plus a squared. That is equal to this, right? Because take it to the left-hand side, right? And the first the common denominator is a, right? And just solve for f, we get this expression. That means that Laplace transform of sine of 18 is equal to a over s squared plus a squared. So in this case, now if you just find the Laplace transform, what is it? What is our a here? A is equal to 2. So it is Laplace transform is equal to 2 over s squared plus 4. Okay. This is how we calculate, guys. We have around 3 minutes left. Let's have break. Maybe after 10 minutes, we will continue. Now I'm going to stop here. Okay. A break, and after 10 minutes, we will continue. See you soon.